Welcome everybody. I'm Tarun Kumar Agarwal. Has recently finished my master's in integrated circuit design from Katholieke University of Applied Sciences, Austria. I did my master thesis on thin films at imec Belgium. The topic of my research paper is study on the lower saturation voltages of dual gate thin film amorphous indium-gallium-zinc oxide metal-oxide transistors. It is a continuation of the previous research work done at imec by Florian and Roose. The further research on a-IGZO TFT demonstrates the early saturation point of dual gate TFT devices. We have two different type of devices. One device is a single gate device and another device is a dual gate device. And the drain current of the transistor is the sum of the forward and the reverse current. Here, for the dual gate devices, the addition of the back gate is assumed in the equation. Furthermore, this current drain current equation is simplified to the linear region equation. From there, we have calculated the saturation point voltage and further evaluates the saturation region equation for the dual gate devices. The reason behind the dual gate devices to saturate at lower voltages as compared to single gate devices is due to the factor of 1 plus zeta in VD saturation point. The 1 plus zeta is approximately to 2. That makes the devices to saturate at lower with drain to source voltage as compared to single gate devices. Furthermore, we try to understand the possible configuration of dual gate TFT devices as a transistor and as a diode. These configurations are characterized, compared, analyzed to understand the dual gate TFT device behavior. The one of the important aspect of the dual gate devices is that if one gate is disabled, the disabled gate still contributes to reverse current, even though it doesn't contribute to forward current, but it contributes to reverse current. Due to this increase in the reverse current of the dual gate devices that saturates the dual gate devices earlier as compared to single gate devices. At the same time, if we look into these configurations, the configuration A saturates much earlier as compared to configuration B. And these characterized results also follow the model. From there, it was clear that the configuration A further saturates earlier as compared to configuration B. So the disabled gate in the configuration A that further reduces saturation voltage approximately by 1 plus zeta. Then we have compared the different diode configurations of dual gate devices. Due to the multiple gates, it is possible to have the 3 different configurations of a diode in dual gate devices. These configuration characterized results are compared with the single gate devices. And we have analyzed that the dual gate as a dual gate diode, if both the gates are shorted with the drain, has the maximum drain current in comparison with all the other configuration. From the characterized results, we have tried to extract the zeta through a new way, and that is assumed to be more accurate at the saturation voltages. Furthermore, the dual gate TFT devices characterize results for the configuration A and B are compared with the model simulation results. This evaluation is to understand the saturation voltage from the characterized results and the comparison with the model results. And we can see that the devices, the configuration B, the two DFT devices, doesn't follow the model for the higher gate voltages due to second order effects of the backgate which increases with the increase in the backgate voltages. In the last section, we are comparing the saturation voltage point with the model simulation result under the different bias conditions. This analysis has made it clear that the dual gate devices perfectly follow the model for the lower voltages than the higher back voltages. From the depth analysis of the second order effects, the characterized results follow the model very closely, although there is a small deviation in characterized results for higher saturation voltages due to second order effects. Thank you for the attention.